In this video, I want to go through the process of getting to the kinematic equations again, but this time I want to start with a calculus method. So this is calculus-based physics, and we did not use any calculus in getting those equations last time. So I want to start from a different spot this time and show that we still arrive at the same four equations with this different method. So for starters, just for reference, we have already said that the derivative of x with respect to time is our velocity, and the derivative of velocity with respect to time is our acceleration. And we said that the kinematics are for constant acceleration only. So I'll go ahead and write that, constant acceleration. If the acceleration itself depended on time, if the acceleration was changing with time, then those four equations that we derived would not be valid anymore. So we have constant acceleration, and we're just going to start with a. So this is our acceleration, and it is a constant, whatever it may be. Now, if you're taking this course alongside calculus, you may not have seen the integral yet. And if you have not seen the integral yet, this video may not make a whole lot of sense. So maybe it would be good to come back and watch it, because I'm not really going to explain what an integral is. If you have already taken calculus, and if you are familiar with an integral, then this might be beneficial. So what we're going to do with a is we're going to integrate it with respect to time. So the integral of a dt. Now, I'm just going to use the constant rule of integration. If I'm integrating dt here, and a is a constant, then this is going to be at, and I have to have my constant of integration. But now look over here. The derivative of velocity was acceleration. And that means if we take the integral of acceleration, so if I were to integrate both sides here, right, that would mean the integral of acceleration with respect to time is velocity. So this expression that we have here is actually equal to the velocity. So I'm going to rewrite that here. So the velocity, and now I'm going to write of t. So I'm just going to write this in a couple places just to show that this is a function that depends on t. So this is c, and I'm going to rewrite it c plus at. I'm going to write it this way. And so this c is a constant of integration, and we want to know what this c is. So I'm going to plug in 0 for t. So at time equal to 0 seconds, then I just get c, because this term right here goes to 0 because t is 0, and so that one just gets canceled out. And so we have v of 0 equals c. Well, if our velocity at time 0 is equal to c, then c has to be our initial velocity. C has got to be our initial velocity because it's our velocity at time equal to 0. So now I can rewrite my velocity expression, v equals v naught plus at. So there's my velocity expression. And you may recognize this. You may recognize this as one of the kinematics. This is one of the kinematic formulas. So we'll call this one 1. Now the numbers may be different on these than the last video. I'm just numbering them so we know how many we have. So that's our first kinematic formula. I'll slide this over here. Now, let's keep going. What if I did the same thing? So what if I took the integral of v with respect to t? Well, v is not a constant, so I'm going to use this expression for v. So this is going to be the integral of my expression for v, the final velocity, or the instantaneous velocity at a given time, is going to be v naught plus at with respect to t. And so if I integrate this, v naught, our initial velocity right here, in any given situation is a constant. If we have a situation or problem, our initial velocity is not going to change. It's just, it is what it is. Whatever we started at is what we started at. So that's a constant. So integrating that with respect to t gives us v naught t. And then integrating at with respect to t, I'm going to use the power rule of integration here. This gets me at squared over 2. And then again, I have to have my constant of integration. I have to have my constant of integration right here. So we're going to do the same thing. We're going to look back up here, and or up here rather. And so the derivative of position with respect to time is velocity. So the integral of velocity with respect to time, which is what we did right here, must be position. It must be position. So this entire expression is our final position after some time t. Now, just like we did above, I'm going to rewrite this a little bit. So this is going to be x equals, and I'm going to put the c out in front, plus v naught t plus at squared over 2. And again, I want to figure out what this c is. Well, I could write this x just like I wrote the v earlier. This x depends on time. It depends on the time. So I could write x as a function of t, and I'm going to see what my position is at time equal to 0. Well, at time equal to 0, I just get c again, because if time is equal to 0, this term cancels out, and this term, a times 0 squared over 2, goes to 0, and so both of these two terms right here go to 0, and I'm just left with c. Well, my position at time 0, that's just my initial position. That's wherever I started at. So here, we have c equals x naught. And so maybe I'll make a little, maybe I will call this, just to distinguish, well, I did it again. Just to distinguish, that's C2, and up here, I'll just label this C1, so we know that there was a difference in these two. And so this is C2 and C2 right here and right here. So my position at time 0 is equal to this constant of integration, but that's just my initial position. So let's substitute that in and go from there. So that's going to be x, and I'm not going to write the of t. We know it's a function of t. So x of t, x as a function of t equals our initial position plus v naught times t. And I don't know why I put parentheses there. It's just v naught t times t plus at squared over 2. And you will recognize from the last video that this is another constant. This is another one of our kinematic formulas. So we have two so far. We have this one here, and we have this one that we just derived here. So in the next video, we'll start from these two to get the remaining two. And notice these are different than our first two from the last video.